Okay, we're going to start looking at limits today, and this will probably take a couple of lessons and a couple of days to go through, but I'll record this in one recording here, and it should be fairly concise, but you can always come back to it later on. So what we're going to look at is what a limit is, how to find it, things like that. So first of all, you can see the equation looks a little bit different. We get this little limit thing out in front, but you can see the rest of it looks like a regular rational equation. And what we're going to be looking at is what does a limit, or what does the equation approach as we get closer and closer to some sort of number. So we'll start with looking back at sequences, and if you remember, a sequence just follows some sort of pattern and it can continue on and on forever. It can go to infinity or it could stop at some point. So both of these, for these two examples that I've got here, they both are just, you can see we're just dividing by 2 each time. We're cutting things in half. So we could actually write the formula as half to the n. So with any kind of sequence that is convergent, which means it's going to eventually approach some sort of number. So like this last one, if we keep on going, you can see our fraction just keeps getting smaller and smaller. So we're basically going to approach 0. Whether we have a finite ending to it or we go to infinity, basically once we get far enough, we're going to say it's going to be approximately 0. And that's what a limit's doing. It's basically saying, what are we going to approach eventually? So it has to be a convergent sequence. Divergent ones won't work, and we'll look at what that case is once we get into some graphing and things a little bit later on. But for now, we're going to look at equations that have a limit in most cases. So we're going to try to figure out what that limit is. So if we look at this first example, we could plug in a half to the power of 5, and that would just equal 1 over 32. So that's still a small number, but not too bad. If we put in a half to the 15, that'll give us 1 over 32,000. So pretty small decimal now, almost 0. And again, on our calculator, we can't plug in infinity, but we could plug in something pretty small. So if you put in 0.5 to the power of, say, even 100 or something like that, your calculator will basically give you 0. So at some point your calculator can't even calculate it. It gets so small, so then it would just round it off. So 100 might not be big enough. You might have to try 1,000 or 100,000 or something like that, but it'll eventually just give you the 0. So what we want to do is, can we actually figure these things out without actually plugging in a whole bunch of numbers over and over again? So what we want to do is follow a few steps. The first step always is to try to plug in the number directly. If it works in the equation, then that is indeed the limit. So for this first one, let's try it. If we plug in a 2, we'd have 1 plus 1 over 2 to the power of 2. So on your calculator, if you type that in, so 1.5 to the power of 2 gives us 2 1/4, or we could round that off as a fraction as 9/4. So what that means is that is the correct limit. So in this case, we're dealing with some sort of location on the graph. So if we were to actually graph this thing out, when x is 2, we actually have some sort of point, a coordinate on that graph, a 2 and 9/4. So that is indeed the limit. So the next example, if we plug in a 4, we would get 7 squared, which is just a flat line. That's just like saying y equals 49. So that means it doesn't matter what our x value is. Our limit is going to be just 49. So again, our graph would just be a horizontal line at 49. So it doesn't matter what we approach. It's always going to be just 49. So the first step is definitely plug things in and see what happens. So let's try that again for these next two. If we plug in a 2, we get 4 minus 10 plus 6. That would give us 0 on top. Plug in 2 in the bottom, we get 2 squared minus 4 is also 0. So we have 0 divided by 0. So that's one of our first cases where we run into issues. If we get 0 divided by 0, we have a problem. So what we have to do is try to do some sort of simplifying first before we plug the values in. So a good strategy is, if you look at it and you see polynomials and things like that, try to factor. So if we factor the top, we would get x minus 2, x minus 3. If we factor the bottom, we have a difference of squares. That'd be x minus 2, x plus 2. So now if we do the limit, we can actually see that our x minus 2's would cancel. So now we can plug in 2 in the remainder, and hopefully it'll work. If we plug in 2, we get 2 minus 3 on top, which is -1. 2 plus 2 on the bottom is 4. So that's it. So that means we do get limit of a quarter, negative a quarter. So in this case, if we tried to graph it, they would be likely a discontinuity point, because that's our x minus 2 factor that canceled. So we're just basically saying what's that point of discontinuity, in other words, and which is saying what's the limit going to be as we get closer and closer to that location. So the next one, let's try this. If we plug in a 4, again, we get a quarter minus quarter, so we'd have 0 on top. And x minus 4, 4 minus 4 would be 0 on the bottom. Again, we run into troubles. This one we can't really factor, but rationalizing or common denominator in the top might work. So let's change the top to be over 4x for both fractions. So our first fraction, we got a quarter, so that means we need 1x on top to balance that out. The second fraction, we got 1 over x, so let's make that 4 on the top, and that should work. So our top of our fraction would simplify to x minus 4 over 4x. All of that's going to be x minus 4. So we can actually bring that up. Let's write that as over 1, and let's multiply by the reciprocal. And we can see that we actually get those factors to cancel out. So all of this will simplify to just 1 over 4x. Now if we plug in the 4, we get 1/16. So that is the correct limit in this case. All right, let's try the last one. Plug in a 9 again, we get root 3 plus 3 would be 6. Plug in a 9 on the bottom, we get 3 minus 3, which would be 0. Remember, 0 is undefined, I can't divide by 0. So again, maybe we're running into these issues. So let's try rationalizing this time and see what happens. So if we rationalize the top and bottom, so in this case we want to times everything by the bottom, root x. Let me erase all of this stuff here. So our rationalized value should be root x plus 3, top and bottom. So if we FOIL out the top, we would get x, and then we'd have 3 root x and another 3 root x, which would be 6 root x, and then 3 times 3 is 9. And then on the bottom, we'd get x minus 3. So now if we plug in 9 on top, does it work? We get, on the bottom we'd have 3 times 3 would be x minus 9, not 3. So let's fix that. So again, if we plug in 9 on top, we will get 9 plus 6 times 3 would be 18, plus 9 again, so we get 36, I think. But you can see we get 9 minus 9, we still get a 0 on the bottom. So originally we had 6 over 0, which doesn't work. Now we're getting 36 over 0, which still doesn't work. So what this basically means is, even though we tried some math, we still didn't solve anything. So when you get something over 0, and the top is not a 0, like in this case we had a 6 or 36, that means basically there is going to be no limit. And we'll see with graphing a little bit later on too what that actually means. But from your Math 30-1 background, when we do get a limit, like the first two, these are discontinuity points. So we're getting like our bullet holes at a certain location. For this last one, what's likely happening is at 9 we've got a vertical asymptote, which is a different kind of a scenario. So we'll come back to this a little bit more when we graph, but for now it's just sort of understanding how you do limits. So you want to plug things in. If they work, great. If they don't work, try to do some factoring or something, and by saying not working, what we're looking for is getting 0 divided by 0. That's usually a sign that we could simplify things. If we get, before we get to these next ones, if we get something that's 0 over 0, keep going, do some work, do some factoring, whatever. If you had 0 divided by a different number, that one we'd stop too. We'd say, well, 0 divided by anything is just 0. And then like we saw, if we have something divided by 0, then that's when we'd say no limit. Okay, so those are sort of our 3 cases so far. So our next type is what happens when we have something going to infinity. So if we put in a value like I have in this first yellow box, you can see if n approaches infinity, that means we'd have 1 divided by infinity if we plug it in. And 1 divided by infinity is basically just like our fraction ones that we looked at, which basically means that's going to eventually round off to 0. So anytime we have limits going to infinity, we want to try to get our fractions to be something over n, and then we can basically say that they're equal to 0. So this first case, we've got, if we plug infinity in, we'd just get infinity over infinity. which is just like 0 over 0, doesn't tell us very much. We need to do a little bit more work. So in this case, we could divide by everything by n. So let's just divide that first fraction by n, divide our second fraction by n, which is still the same thing. Now you can see the n's would actually cancel, so we'd have just 3 minus 2 over n. So now when we do our limits, we could plug it in now, so we get 3 minus 2 over infinity, which would just be 0. So 3 minus 0 equals 3. So that would be our correct limit for that equation. This next one is the same scenario, it just looks a little bit different. So what we're saying here is if we have a fraction to infinity, that's also going to be equal to 0. So you can see it's kind of the same thing, going 1 divided by 0 or 1 divided by a number to the infinity. Those are both the same. So they're just different ways of writing the same sort of thing. So if you see fractions or decimals to the infinity, you can just assume those are 0. So this whole part here will be 0, so we'd have 4 times 0, which would be 0. So in this case, our limit as x approaches infinity would be 0. Okay, our last one, like we said, infinity over infinity is a problem. So 0 over 0, do some work. Infinity over infinity, do some work. A good strategy to do when you get polynomial type things. It's pretty hard to simplify sometimes. So a good strategy is just to divide by the highest power. So for this first example, you can see our highest power is x. We already did one kind of like this, but we could rewrite it a little bit differently. We could just divide everything by x. So you can see our first fraction would simplify to just be 1. So we have 1 over 4 plus x over 1 again. And if we plug in our infinity now, 4 over infinity would be 0. So we just get 1 plus 0 over 1, which would be 1. So it's a good strategy to do when you get one of these kind of scenarios. So in this case, this next one, let's divide everything by x cubed. And if you remember, really what we're doing is we're basically just finding horizontal asymptotes. So if you remember that from 30-1, and we're going to get to more of this a little bit later on as well, but that's really all we're doing with these fractions. By dividing by the highest power, we're basically just finding the horizontal asymptote. So you can see for this one would cancel, so we just get a 3 on top. This one would be, we would get 2 over x, and our last one we still have our 5 over x cubed. And then on the bottom we just get a 2. And then 3 over x squared and 4 over x cubed. And again, those ones that are being divided, so when we do our limits now, when we plug our infinity in, that one's going to be 0, that one's going to be 0, and so are those ones on the bottom. So in this case, our final answer is just 3/2. So if you want to use the shortcut, right, we have 1 over 1 in this case, so 1 divided by 1 gives us our limit of 1. Here we have our x cubes, divide those highest powers, we do get 3 over 2. So our horizontal asymptote ends up being the same thing as our limit for these kind of cases. So the last one, if we divide everything by x to the 4th, you'd see we get 7 on top, then we get 0 and 0 for the rest. This one, when we divide by x to the 4th, we're also going to get a 0. So in this case, we get 7 divided by 0, and just like that one we did on the previous page, you can't do those, can't divide by 0, so we just say no limit in this case. And that's it for limits. We'll do quite a bit more of this in class over the next day or so, and we'll look at lots of different examples to help you practice with the factoring and rationalizing and all that. And that's all.